Alright guys, in this tutorial we are going to do a Kruskal-Wallace test, which is a non-parametric test. It does not assume that there is a normal distribution to your data set. So what you want to do is open up your Kruskal-Wallace datasheet that's posted on Blackboard, and the first thing that we want to do is rank all of the values. Now when we say rank the values, we mean order them from lowest to highest. So the first thing that we have to do is sort the values. So we're going to select the data and sort the values. Now we have to rank them, and we want to rank them from 1 to whatever the number of data points are. So in this case there's 30 data points, right? Because there's one header up here, and so there's a total of 30 data points. So we want to rank them from 1 to 30. So let's just type that right here, 1, 2, 3, 4. We want to rank them from 1 to 30. Now, if each one of the data points was perfectly unique, then this rank in column D would work perfectly. However, the problem is that there are many ties in our data set. So there's 2 zeros, and there's 4 ones, and there's 2 4s, and 2 9s, and so on. And so what do we do with those? Why should this 0 get a rank that's higher than this 0? And it shouldn't. And so what we have to do whenever we have ties is, of course, we have to give them the average of the rank. So we want to give them the average of 1 and 2, which is 1.5. So the average of 1 and 2 is 1.5. So we're not going to give this one 1. We're not going to give this one 2. We're going to give both of them a rank of 1.5. We have 4 ones. So we don't want to give them the ranks of 3, 4, 5, and 6. We want to give them the average rank of 3, 4, 5, and 6. So average of 3, 4, 5, and 6, which should be 4.5. So we want to give each one of these a rank of 4.5. Now we only have 1, 2, and so that's fine. We can give that one a rank of 7. And you might be like, well, why don't we give it a rank of 5? Well, because this one should be ranked 7. We just don't have a 5 and a 6 because we had ties up here. So this one gets a rank of 7. These, we have a tie here, so they get the average of 8 and 9, which is 8.5. Here we have the average of 10 and 9, so we get 10.5. We have 2 10s, so we get the average of 12 and 13, which is 12.5. We have 1 11, so we can give that one 14. We have 1 13, so we can give that one 15. We have 4 20s, so we have to give that the average of 16, 17, 18, and 19, which is 17.5. So each one of them gets an average rank average of 17.5. We have 3 23s, so they get the average of 20, 21, and 22, which is 21. We have the 124, so we get that to be a rank of 23. We have 125, so that's a rank of 24. We have 127, that's a rank of 25. We have we have 3 28s, so that's an average of 26, 27, and 28, which is 27. We have 129, which is 29. And we have 132, which is going to be our 30. And there we have it. All right, so we have successfully ranked all of the values. Now, as long as you didn't put averages into here, we can just go ahead and delete this. If you do have like averages, so if you did average, let's say of 1 and 2, like that, and you tried to delete this, you're going to get a problem here because now this is a function that's not referencing anything. So you're going to have to copy the data values and paste them as values. All right, I'm just going to type in 1.5. The next step is to create a pivot table where we sum the ranks for each one of the treatments. So we're going to put this into an existing worksheet, and we want to move the treatment to rows and the rank to values. And normally we change this to average, but in this case we want to keep it as the sum. We want that sum. So go ahead and copy this data outside of the pivot table, because now we want to change this to say count. And we're going to copy that outside of the pivot table. And now we don't need this pivot table anymore. We can delete it. Because what we want to do now is square each one of the rank sums again, square it using the little caret symbol. And we can just drag that down. And then we want to divide that squared sum by the count. So we're getting an average ranked squared sum. And we can just do that down. All right, so once again, that's the squared sum divided by the count. All right, and we're just going to drag that down. All right. Then we want to calculate a chi-squared statistic, not a chi-squared, a Kruskal-Wallace statistic. Sorry, Kruskal-Wallace test statistic. And the way that we do that, the equation is in the Word document. The way that we do that, follow along, equals, in parentheses, 12 divided by, and in parentheses again, the number of unique data points, which in this case is 30, times 30 plus 1, 31. All right, don't do this, because that's going to multiply 30 times 30 and then add 1 to that, which we get 91. We don't want to do that. We want to multiply, or 30 times 30, that's 900, and then add 1, which is 901. No, we don't want to do that. We want to multiply 30 times 30 plus 1, or you can just type out 31. All right, and then multiply that by the sum of your average rank sum, this last column here, and then subtract 3 times 30 plus 1. Don't do this, because that's going to multiply 3 times 30 and get you 90, plus 1 is 91. No, you want to do this. So 3 times 31, so 93. And of course, you could just type out 31 if you wanted to. And there is your Kruskal-Wallace test statistic. Then what you want to do is go to Google and type in chi-squared table. And the first one that comes up, that's fine. All right, go to that one. You want to look up the degrees of freedom, and I neglected to say that the degrees of freedom is going to be the number of unique treatments minus 1. So there's 5 unique treatments, minus 1 is 4. So we go to the degrees of freedom of 4, and we go over to 0.05. The value is 9.488. So again, we go to 4, which is the degrees of freedom, the number of treatments minus 1, and we go over to 0.05, and we get 9.488. So let's go to Excel, 9.488. If our test statistic that we calculated is greater than the value that we looked up in the table, we can safely say there are significant treatment differences in our analysis. That's it. If you want to do this in R, it's very simple. Let's go open up RStudio. And let's bring in the data set. Now I'm bringing it in via the clipboard. So I want to copy the data, just so we can just copy the treatment and the value. So the data is now in R, and all we have to do is run a Kruskal-Wallace test like this. Kruskal.test. And we'll say value is predicted by treatment, and the data is equal to my data, or whatever you called it. Press enter, and the chi-squared value is going to be slightly different. I'm not exactly sure why, but the degrees of freedom is correct and the p-value is correct. And that's all you have to do. So let's go through the second example together. Now, for those of you that were in class, you know that I did not solidify the data, and so everybody had a slightly different one. I did go ahead and I copied them all as values here, so they're not going to change on us. So let's go ahead and rank the data. The first thing that we have to do is sort. And in this case, we're asking people to rank how much they like a donut based on a scale from 1 to 10. Okay? So we rank the data, and in this case, we have 40 data points. So we're going to create a list from 1 to 40. Like that. And as before, we want to take the averages whenever we have a tie. So here we have 3 1s, so we take the average of those. We have 5 2s, so we want to take the average of all of these, which is 6. 3 3s, take the average of 9, 10, and 11, which is 10. 4 4s, or 3 4s, so we want to take the average here, which is 13. 1 5, so that's 15. 4 6s, so the average here is 17.5. There are 6 7s, so the average is going to be the average here, which is 22.5. There are 6 8s, so it's the average right here, which is going to be 28.5. There are 4 9s, it's going to be the average of these values, which is 33.5. There are 5 10s, so it's going to be the average of these values right here, which is 38. Now, one way that you can know if you've done this correctly or not is if you sum up all of these values here, you should get 820. Well, if you sum up all of these values here, you should all get the same exact thing. All right, well done. Now let's go ahead and insert that pivot table. So these are the ranks. Now here, if I delete this, we get a problem because I did an equation there, so I'm just going to replace that with 2. Let's create a pivot table around those ranks. Insert pivot table. Let's put it into the same worksheet. And we'll summarize ranks by donut type. And again, we want to keep it the sum. And now we want to get the count. And then we can get rid of this pivot table. We don't need it anymore. Let's go ahead and get the squared value of those rank sums. And now let's get that average. And now we are ready to calculate our Kruskal-Wallace test statistic. Great. Let's do it together. Is equal to 12. And 12, we don't get 12 anywhere. 12 is in the equation. 12 divided by, there are 40 replicates, total replicates, so 40 times 41 times the sum of these values here minus 3 times n plus 1, which is 41. And there's your test statistic. Let's go over to the chi-square table. There are 4 treatments, so our degrees of freedom is 4 minus 1, or 3. So let's go over to the table, 3, and we go over to 0.05, which the value intersecting is 7.815. Is this significantly different? Yes, because our Kruskal-Wallace test statistic is greater than the table value. Let's go ahead and do this in R. I'm going to copy that data and bring it over to R. And again, I'm going to call it my data read.dlim. Great. So it's in there. Now we'll go ahead and say Kruskal.test, and it is number of people is predicted by donut type. Data is equal to my data. And sure enough, We again get a chi-square that's slightly different from what we calculated here, which is 18.879. It's okay, but the p-value, the degrees of freedom is correct, and the p-value is also going to be correct. And there you have it.